Hello everyone. So in this pre-lecture tutorial we're going to introduce the common ion effect and then apply it to the study of chemically buffered systems. And so really the best way to discuss the common ion effect is to work through an example and also make some comparisons quantitatively to systems that do not have the common ion effect applied to them and those that do, so that you can actually see how the common ion effect works. So let's take this example that we've got on the screen right now. I'm being asked to calculate the pH of a solution that I prepare by dissolving 0.37 moles of formic acid and 0.23 moles of sodium formate in water so that I get 1 liter of solution. And as part of the background information of the problem, I'm also given the acid dissociation constant, the Ka, for formic acid, and that's 1.77 times 10 to the negative fourth. And so, since we're being asked to consider formic acid, a good place to begin is to actually write an equation for the partial dissociation of formic acid. So, I'm going to write that out here. So, formic acid, being a weak acid, should partially dissociate in an equilibrium process to protons and the formate ion. Now, the other thing to keep in mind is notice that I'm actually going to be adding two things into this solution. I'm going to be adding some formic acid, and I'm also adding a salt that contains the formate ion. So sodium formate, since it's a soluble salt, will dissociate into sodium ions and these formate ions. And since that dissociation process, which I'll show up here, is a 1-to-1 process, then basically what I'm going to get is a 1-to-1 relationship between the concentration of the sodium formate and the concentration of the formate ion I get after dissociation. So I'm going to incorporate that into an ice table. And fortunately for us, this problem has a 1 liter volume of solution. So that means that these amounts of substance in moles will also be the molar concentrations of each of these substances. So that would mean I'd have 0.37 molar formic acid to begin with, and I'm also going to have 0.23 molar sodium formate to begin with, and initially no protons. Now, because I still don't have any protons, this equilibrium is still going to proceed to the right, which means that I'm going to be losing some of the formic acid, but gaining each of the species on the right-hand side of the equilibrium equation. And then if I go ahead and add each column of the table vertically, then I get the following expressions for the equilibrium concentrations of each of these species. So if I consider Ka, Ka should be my proton concentration times my formate ion concentration over my formic acid concentration. And if I go ahead and insert my equilibrium concentration expressions from the ice table, I get the following. And this is all going to equal 1.77 times 10 to the negative fourth, because that was the given value for the Ka. Now, since this Ka is somewhat small in comparison to the initial concentration of the formic acid in particular, then I'm going to go ahead and make our assumption that X is small. And so what that does is it makes it negligible compared to this term up here, the 0.23 plus X, and also the difference term, much like we've been seeing over the past couple of chapters since we started studying equilibrium. So that means that this will simplify to X times 0.23 over 0.37, and that's going to equal 1.77 times 10 to the negative fourth. I'm going to go ahead and solve for X, and if you do the algebra properly, you should get 2.8 times 10 to the negative fourth molar. Now again, I still want to check this assumption, so I'm going to go ahead and calculate the percent ionization. And so that's going to be 2.8 times 10 to the negative fourth, and I'm going to divide by the initial concentration of the formic acid, and then multiply by 100. If I go ahead and do that math, I end up with 0.077% ionization. So that means that my assumption is valid. So that means that if I'm going to calculate this pH, X would equal my hydrogen ion concentration. pH is equal to negative log of the hydrogen ion concentration. If I plug in, that's a negative log of 2.8 times 10 to the negative fourth. Okay, if I do that math, I end up with 3.55. Now, in order to really appreciate the common ion effect, I think probably the best way to see how the common ion effect affects equilibrium processes is to actually go ahead and calculate the percent ionization for the 0.37 molar formic acid solution alone. So this would be just in water. So instead of having this formate that I had in my problem, I'm going to treat this as if it were a solution of weak acid, which is the system that we were studying in chapter 16. So if that's the case, I would go and I would set up my ice table once again. And again, I have an initial concentration of 0.37 molar. And since I'm making the assumption that this formic acid exists in water without the formate being present, then it's a lot like the problems that we were doing in chapter 16, where I don't have any of my formate or of the protons, and I'm going to lose some of the initial concentration of the formic acid, but gain some proton concentration and also some formate concentration. I would get the following for my equilibrium concentrations for all of the species involved in the reaction. If I go ahead and plug these equilibrium concentration expressions into my expression for Ka, then I get x squared over 0.37 minus x, and that is 1.77 times 10 to the negative fourth. And again, I'm going to make my customary assumption that x is small, again based on the small value of the acid dissociation constant. And if I do that math, as we did in the previous chapter, I get x squared is equal to 6.549 times 10 to the negative fifth, and then I would take the square root of both sides, and in this case x is 8.1 times 10 to the minus 3 molar. And so once again I'll calculate the percent ionization, right, for two reasons. One is to check on this assumption that x is small, but also to illustrate what the common ion effect does to equilibrium systems. That would be 8.1 times 10 to the negative third molar divided by 0.37 molar times 100. And this time I get 2.2% ionization. So my assumption was valid. But the other observation that you should make is notice that the percent ionization is much greater when the formic acid is alone without the formate. But once I include the formate, basically that reduces the extent of ionization. Basically what it does is it still causes the equilibrium to shift to the right, but the extent to which the equilibrium shifts to the right is decreased because you already have some initial formate present. And so that's sort of the idea behind what happens with the common ion effect. Now, the reason why this is an important topic is because it allows us to understand buffers. Now, essentially what a buffer is, it's a solution that contains roughly equal concentrations of weak acid and a conjugate base. And what that does is it creates a system that resists changes in pH when you add small amounts of strong acid or strong base. So take, for example, if I have this problem here. All right, I'm going to prepare a buffer by combining 50 milliliters of 1 molar potassium acetate with 50 milliliters of 1 molar acetic acid. So if I go ahead and consider the partial dissociation of acetic acid, I'll get acetate ion and protons in this equilibrium process. I'll go ahead and start setting up my ice table. Okay, and we know enough about concentrations now that I'll leave it to you to verify that based on this information regarding the preparation of the buffer, I should begin by having 1/2 molar acetic acid and 1/2 molar acetate, but none of my protons yet. Okay, basically, if I wanted to calculate the pH of this buffer, then I would have to go and do what I did for the common ion effect. Again, because there still is no proton present, or there are no protons present at the start of this equilibrium process, then I'm still going to lose some of the acetic acid, but gain acetate and gain protons. And that would lead to the following equilibrium concentration expressions. And essentially what's going to happen is if I go ahead and plug these in to the acid dissociation constant expression, and set that equal to my Ka value, I should get 0.500 plus x times x divided by 0.500 minus x. And that's 1.76 times 10 to the negative fifth. Again, if I make the assumption that x is small, I end up with 0.500x over 0.500. Well, the 0.500s would cancel, and that just means that x is 1.76 times 10 to the negative fifth molar. Again, I'll calculate the percent ionization to check this assumption. So that's 1.76 times 10 to the negative fifth molar divided by 0.5 molar times 100. And I get a percent ionization this time of 3.52 times 10 to the negative third percent. So clearly much smaller than 5%. So that means that this assumption is valid. That means that my 1.76 times 10 to the negative fifth molar is a proper estimation of my proton concentration. And calculating the pH by taking the negative log of the hydrogen ion concentration, I would actually get a pH of 4.754. But the important thing to note about buffers is, since I have some initial concentration of acid, if I were to add base to this solution, well, the acetic acid would neutralize that base. Okay. Now, if I were to add acid, the acetate ion being the conjugate base, it would neutralize the acid. And so, in that way, this acetate buffer is actually able to resist changes in pH when I add strong acid or strong base to it. Now understand, this has its limits. It is possible to overwhelm buffers, and that gets into the topic of buffer capacity, which we'll discuss in class. We'll also discuss alternative methods for calculating the pH of buffers and calculating how to find out how to prepare buffers by figuring out how much of a reactant to mass out on a balance. All of these things we'll discuss in class, but for now, work on the follow-up assignment, and we will see each other in class and discuss this further then. Okay? Have a good night.